All right, today we're going to break down one of the most fundamental ideas in all of modern technology, the CAP theorem. You can think of it as this hidden rule that secretly governs pretty much all of the massive computer systems that we depend on every single day.
Have you ever stopped to wonder how your social media feed is always somehow updating? Or how your banking app manages to stay online even when you know things must be going wrong somewhere behind the scenes? It's something we totally take for granted, but the answer is actually pretty fascinating.
And the answer really boils down to this one core concept: trade-offs. You just can't have it all the time. To keep these giant services up and running, engineers have to make some really tough choices. And that's exactly what we're going to dig into today.
Okay, so to really get this, we first have to talk about something called distributed systems. Just think about it for a second. Your bank doesn't run on just one giant computer somewhere. No way. It has a whole network of them, right? Maybe thousands, spread all over the place as ATMs, servers, databases, you name it. Same thing goes for your favorite social media app. That whole interconnected web, that's a distributed system.
And this is where it gets really interesting. See, in a perfect world, all those computers are just chatting away, perfectly in sync. But we don't live in a perfect world, and networks are definitely not perfect. They fail. A connection can drop between two data centers, and that creates something called a network partition. And that is the moment of truth for any distributed system.
And this is where the CAP theorem comes into play. It gives us a simple but really powerful way to think about how to handle those network failures. And it's all built on three core ideas: C, A, and P.
First up, we've got C for consistency. This one's pretty straightforward. It just means everyone sees the exact same, most up-to-date information at the same time. If you take money out of one ATM, another ATM on the other side of the country instantly knows your new, lower balance. There's no confusion, just one single source of truth.
Next is A for availability. This one's all about being always on. It means no matter what, when you make a request, whether it's checking your feed, posting a comment, or looking at your bank balance, you will always get a response. The service just doesn't go down. And finally, there's P for partition tolerance. This is the system's ability to keep on chugging even when those network failures we just talked about happen. When parts of the system just can't talk to each other. And for any modern, large-scale system, this isn't really a choice. You have to be partition tolerant because networks will inevitably have problems.
Okay, so here's the big reveal. Since we have to accept that network partitions are just a fact of life, the CAP theorem basically says that when one happens, you are forced to make a choice. You absolutely cannot guarantee both perfect consistency and perfect availability at the exact same time. You have to pick one to prioritize over the other.
And this lays out that choice perfectly. So what do? Do you go for consistency, where you promise that the data is always correct, but you might have to tell the user, sorry, try again later? Or do you go for availability, where you promise the user will always get a response, but you have to accept that for a little while, the data they see might be just a tiny bit stale?
I know this can all sound a bit abstract, so let's make it way more concrete. We're going to look at how this exact trade-off plays out into two very, very different real-world systems. And we'll start with something we all understand: a bank. So, in a perfect world, a bank's system is just a beautiful model of consistency. A customer walks up, withdraws some cash from one ATM, and boom, the balance is updated everywhere instantly. Another ATM 100 miles away shows that new correct balance. Everything is perfectly in sync. But then, the worst happens. That network connection between the two ATMs breaks. Suddenly, they can't talk to each other. We have a network partition. And now, the bank has to make that tough CAP theorem choice. Now, what's really fascinating here are the stakes. They're huge. If the bank chooses consistency, well, it has to shut the ATMs down. Sure, it's annoying for customers, but the money is safe. But if it chooses availability, the ATMs stay online. But now there's a risk that a user could literally withdraw their entire balance from both machines before the system can catch up. For a bank, the choice is pretty clear, right? They will almost always choose consistency. Okay, so now let's flip the script. Let's look at a social media platform. Imagine that same network partition happens right in the middle of a viral post with a super active comment thread. Choosing consistency might mean they have to turn off commenting for everyone until the network is fixed. But choosing availability? That means people can keep commenting, with just a tiny risk that for a few moments, you and your friend might see a slightly different version of the comment thread. For most social apps, that's a risk they're willing to take to keep things running. So it seems pretty simple, right? Banks choose C, social media chooses A. Case closed. Well, not quite. As with most things in engineering, the reality is actually way more nuanced than that.
Because, yeah, the real world is messy, and the choices that engineers have to make are rarely that black and white.
What modern system designers have figured out is that it isn't about choosing 100% availability or 100% consistency. They can actually operate in this fascinating gray area, making really smart, fine-grained decisions about which parts of a service to prioritize.
Let's go back to our bank for a second. During that network partition, instead of just shutting the whole thing down, they could use a much smarter hybrid approach. Like you see here, checking your balance, that might still be allowed. It's low risk, and it keeps the service available. They might even let you make a small withdrawal, but trying to take out a large amount of cash or make a deposit? Nope, those are blocked until perfect consistency could be guaranteed again. It's a really clever way to manage risk while still providing as much service as possible.
So, you might be thinking, if the real world is so complex, is the CAP theorem even still useful? And the answer is absolutely. But it's really important to understand what it is and what it isn't.
So, what are the big takeaways? First, think of the CAP theorem as a mental model, not some strict, unbreakable law of physics. It's an incredible starting point for designing any distributed system, because it forces engineers to confront those hard questions about trade-offs right from the beginning. It makes them ask, when things inevitably go wrong, what do we care about most? But it's important to remember it's not the whole story.
And that leads us to one last, really interesting question. The CAP theorem is all about what to do when the network fails. But what about the other 99.9% of the time, when everything is running just fine? Well, it turns out, even then, there's a whole different set of trade-offs to think about, usually between things like speed and consistency. But that's a story for another day.